So far we have been talking about mostly value function based approaches for solving solving RL problems, right. So whether it is Monte Carlo or TD or whatever, right. So it has been value function based, and there is a very small fraction that we looked at policy gradient methods, and there was a reinforced algorithm we looked at, but we never talked about how would you use policy gradient for solving the full RL problem, right. We only talked about it in the context of immediate RL, right. So I will come back to that at some point. I will talk about policy gradient methods for the full RL problem, right, and perhaps before that I will do a little bit of average reward reinforcement learning before we get on to that, right. But except for the policy gradient part, right, and the linear bandits, right, except in those two circumstances we have essentially been using some kind of a lookup table representation for our value functions, right. Whether it is a bandit case where we kept a q of a, right, or when we talk about v of s or v of or q of s comma a, right, we have always been assuming some kind of a tabular representation, right. For every s I know what the value is, right. So I have been looking at some kind of a tabular representation. So what are the problems with this tabular representation? So what are the drawbacks of using a lookup table? Are there any drawbacks for using a lookup table? Memory, right. So yeah, good. For the time being, let us assume that okay, we will come to this. So first question is memory. Okay. Next problem is handling continuous states. Right. Then anything else? You are not allowed. For the remainder of this class you are not allowed to answer questions. No, people are wondering, we just had this discussion yesterday in the lab meeting. So in fact he is using a cheat sheet. Let us suppose that memory is not an issue, right. So we have huge RAM machines, so 1 terabyte RAM is not uncommon now, right. Let us say that I build a very large memory machine, right, or I use some external memory algorithms or something. All you need is some kind of a large table data structure, right. You need to have a data structure that can handle very large tables, and in fact there actually exists external table storage libraries, right, that allow you to handle tables as large as your hard drive, right. So let us say memory is not an issue, right, and let us say continuous states is also not an issue. I am leading up to something else, right. So I have discrete states, right, I have a lot of them, fine, but I also have a lot of memory that I can store these things, right. So what else could be an issue in having a lookup table representation? Was it? Query time could be high, okay. Yeah, something non-implementational. Maybe I shouldn't say it's non-implementational, but something non-system level answer. And guys who know machine learning, who have been in the ML class and things like that, should have an answer for this, even if not others. Huh? No. Come on. Okay, so what are we talking about here? We are talking about functions, right? We are talking about value functions, right? We are talking about state value functions and action value functions, so V and Q. So we have learnt about functions, right? In machine learning we have looked at functions, right? So have you ever used a lookup table for learning a function from data? What do we do? Huh? Use some parameters and try to estimate those parameters. So why did we do that? So how does learning work, right? I give you a set of data points, right, and from those examples you are supposed to induce forms of functions that allow you to answer questions about points you have not seen already, right. So why does it become important in RL? If I have lots and lots of states, I have a huge table, and if I am using the classical lookup table version of things, then unless I have visited that state not once, unless I visited that state often enough, I do not have an estimate for that value function, right. That means if I have like a million states, or million is small, right. So in fact there is one problem which I implemented some algorithms on during my PhD, which had 10 power 25 states. Right, and if I have to experience every state in that multiple times, I would still not have graduated, right. So we need something else, right. So we need to be able to generalize. I feel like a dentist. Extracting answers is like extracting a tooth from you guys. I mean, anyway, fine. Let's go back. So we want to generalize, right? That is very crucial. So to achieve all of these, what do we do? Instead of representing the value function as a lookup table, we try to represent it as some kind of parameterized function, right. So the most popular choice for the last couple of years has been to use a neural network, right. Use a neural network, an artificial neural network as your parameterized representation. So what are the parameters here? They will be the weights of the neural network, right. So speaking of which, so a pretty momentous thing happened a few minutes ago. So how many of you, did you follow the AlphaGo thing? It won, yeah. So AlphaGo won against the highest ever rated human master in the game Go. So remember I told you about AlphaGo, which is an RL and deep learning based Go playing agent. It just, so the matches have started in Seoul, right. So this guy is a Korean who is the highest ranked ever human in Go, and the first game AlphaGo won, right. People are actually stunned, even the DeepMind guys did not expect to win, right. The company who made this thing, they just wanted to see how close they can run the human, right, and they won. Maybe he was sick or something, I do not know, so we will see. So it is a 5-match series, $1 million prize money. They probably win it and then donate it to some charity or something. But anyway, so that's amazing, right. So and that uses a neural network for representing the value function, okay. So the parameters we talk about here are your the weights of the neural network, right. It could be any kind of weights, thresholds, right, and other parameters, slopes of the transfer function, whatever, right, however complicated you want to make the parameterization, right. So that's typically what we do. So this kind of parameterized representation obviously comes with a cost. So what is the cost? What's it? There will be some kind of underlying bias, and what does the bias deal to? And it leads to some kind of approximation, right. So as soon as I move into this kind of a parameterized representation, unless I make the parameterization so powerful that any value function that I want to represent I am able to put it in here, which will be kind of defeating the purpose, right. I will be essentially end up with as large a state space as I originally had, right. I mean, so if you think about it, the lookup table itself is a parameterized representation. What are your parameters here? Each entry, yeah, value of each state itself is a parameter, right. You can just think of that as a parameterized representation, right. So if I make my parameterized representation complex enough that it can represent any value function without any loss, right, then the number of parameters I will need will essentially be the same number of entries as the lookup table. So I will not have saved much, right. So you essentially you want a simpler representation, you do not want something that has as many parameters as the lookup table, right. You want something that has a lot fewer parameters than the number of states, and per force you have to accept an approximation, right, because I will not be able to model every value function defined on some state. So, I will have to essentially accept some kind of an approximation. So, this is also known as right. So, people call this function approximation, RL and function approximation and so on and so forth. The chapter itself is called in the new book I forget what, on policy evaluation with function approximation or something like that. So, that is the title of the chapter, right. Unfortunately, since the chapter is not edited, it also talks about control in the same chapter, and the second chapter is called on policy control with function approximation, and it is empty. The 10th chapter is called on policy control with function approximation, it is empty, and the on policy evaluation with function approximation talks about both right now, correct. Yeah. So, but it is called function approximation. Essentially, you can use this as synonyms, right. You can say I am using a parameterized representation or function approximation, typically are used synonymously, okay, great. So, what is going to happen? So, I have my true value function, say V pi, right. So, I am going to approximate that by some function V hat, which is defined by a set of parameters theta. So, we looked at this notation earlier, right, in reinforce. When we looked at reinforce, I looked at this kind of a notation. This, when I put a semicolon and write something to the right of the semicolon, it is a set of parameters, to the left of the semicolon is the argument to the function, okay. And great. So, what should be the criteria for deciding on what V hat should be? There are multiple things I need to do here, right. So, for the benefit of people who have not done ML, right, there are at least two stages that I need to proceed here. The first stage is deciding
error function to see how close you are to the value function.
That is the second stage. The first stage is deciding how the output is going to depend on theta. Right. I am saying that some set of parameters, right, there must be some functional form associated with this set of parameters. I said neural networks, that is one functional form, right. So, parameters are the weights, right. I can very simply write V hat of S semicolon W, but how do those W determine what V of S is, right. So, that is some kind of a connected neural network. I can talk about 3 layers, 4 layers or 150 layers. I mean, if you work for Google or Microsoft, you can start talking about 130 layers of a neural network and things like that, right. So, how do I, this is called deciding the functional class, right, or deciding on the class of models that you are going to use for representing this, right. This is the first thing. What is it that I am going to do? I can use decision trees, right. I can use regression trees. In fact, people have used regression trees for representing value functions, right. So, that is one option, right. I can use some kind of complex aggregation, state aggregation. I will talk about that little later, because that is a very popularly used function approximator, right. And we can use neural networks. Another very popular function approximator is just to use some kind of a linear parameterization. So, what I mean by that? So, I will have theta 1, theta 2, theta 3, and then it will just be the weight, and then I will assume that my state is represented by some features, right. If it is a grid world, it can be the x coordinate and the y coordinate, right, or if it is some kind of a robot, it can be the x coordinate, the y coordinate, the angle, the velocity which the bot is moving, right, and the angular velocity and all of those things, right, x velocity, y velocity. There could be a vector of features, right. Let us say that my state is represented by some vector, right, phi. So, phi 1 of S will be the x coordinate, phi 2 of S will be the y coordinate, and so on and so forth, and my value of a state will be phi transpose theta, right, theta 1 phi 1 plus theta 2 phi 2 plus theta 3 phi 3 and so on and so forth. That will be my value function. This is called a linear parameterization, right. So, what we will do later, right, is explore linear parameterization in more detail, but this is a very popular kind of parameterization. I can basically, the first thing I have to do is decide on what is the class of functional approximation I am going to look at, right, and what is the second thing I have to do. So what is the second thing I have to do?
And decide how close you can get.
Right, so I need a error measure, right, to figure out what is the performance measure I am going to use, right, and in some sense this can be common across different choices of parameterization, right. It need not depend on the choice of parameterization. What error measure I use need not depend on the choice of parameterization, but what would potentially depend on the choice of parameterization is how do I find that theta that minimizes this error measure. Okay, so there are three things now, right. So first thing is find out the family of functions that I am considering, whether it is a neural network or decision tree or whatever. The second thing is, well, figure out what is the error measure, how I am going to decide that I have a good approximation to the function, and how am I going to find that theta, how I am going to find the theta that gives me this good approximation. Okay, so that is basically the setup for us. These are the questions that we will have to ask, right. And so what do you think is a good measure? Least squares. Least squares is good enough? Well, it is regression, what else you want, right. So least squares is pretty good enough, right. So how will least squares work? Least squares is a target that I want, right. The performance measure itself would be mean squared error, mean squared error, right. So essentially what I will be looking at is if it is continuous I am going to have a integral there. Is this fine? Yeah, so I left a significant gap here, so that should mean something other than 1 by n within the summation, right. Is 1 by n fine? So what is the problem with 1 by n? So we said mean squared, right. So mean, so you have to take the mean of the square of the errors obviously, right. So if I do it by 1 by n, what does it mean? That is a different mean, yeah. So what does it mean? Huh?
It's uniformly weighed.
I am weighing each state uniformly. I want to get a good approximation everywhere, right. That is what I am trying to do, right. When I do 1 by n, I am trying to get a good approximation everywhere, right. If you remember the expected error computation that we did in, how many of you were in ML? Good number, right. Okay, yeah. If you remember the expected error computation in ML, this you have to cast your mind back to like the 3rd class or 4th class in ML, right. How did we write down the expected error computation there? Weighted by the probability of that particular pair occurring, right. So likewise, and then what we said, we assume that the data is coming to us actually from the probability distribution, and therefore we can do the empirical mean. We can just divide by 1 by n, because if a data point is more likely, we will assume that it appears more often in the sample that is given to you, right. That is how we ended up justifying using 1 by n, right. Likewise, what would be the probability here? So we are lucky in one way because we have a pi here, right, and therefore I am going to write some new quantity here. Any guesses what that is? Huh? How many times? No. Huh? Close. Elect guys. That is a technical term for it. Yeah, that is what it is, but it is called the let's step back again. I have an MDP, I fix a policy pi, right, and then I am looking at the evolution of the system. What is it going to be? Mathematically it will be a Markov chain, okay, it is no longer an MDP, right. So what do you think d pi of S is? The steady state distribution under the policy pi, right. So essentially it becomes a Markov chain. If I keep running the Markov chain for a long time, right, very long time, it is going to settle into some visitation patterns, right. So the steady state distribution essentially tells me, if I steady state probabilities essentially tells me, if as t tends to infinity I sample a state, I stop the Markov chain running and I sample a state where it stopped at, right, the probability that I will find it in that state, that is essentially what d pi s is.
So can you explain how you went from the MDP to a Markov chain?
Well, I do not have any decisions to make anymore, right, my pi is fixed. So when I come to a state I just toss a coin, pick the pi action according to the pi and I go on, right, my pi is not changing. So if I look at the overall transition dynamics, right, it will just look like a Markov chain, right. In fact we did this when we did that convergence proofs, right, for like Bellman equation. So we defined the transition matrix itself, I took out action out, if you remember I wrote p pi of j comma I or something, j comma s. So when we did that we took out the effect of the policy there, we essentially wrote the Markov chain dynamics back then, right. So essentially that is what we are doing here again. So d pi s is the steady state probabilities of state S under the policy pi. So it essentially tells me that the states that I am more likely to visit under this policy, if I keep running this policy often, those are the states for which I want the approximation to be good, okay. Now let us go back to our sampling case. If I am trying to, instead of knowing this d pi s, if I am trying to solve this using sampling, right. So what am I asking for here? What kind of sampling am I asking for here? You are allowed to answer this question. On policy, right, because I expect on policy samples. I do not want you to give me arbitrary states, it has to be sampled according to the policy pi, because only then it will approximate the d pi s, okay. So I am just building up, and we have talked about all of these things individually, but you can see that it all hangs together. Even when I am doing functional approximation, right, when I am doing this is the thing I want to optimize. So I can do it like this. Take that as my error measure, right, provided these were all sampled, S1 to Sn were sampled along a trajectory generated by using pi. Okay, make sense? Good. So now we have an optimization, we have a least squares setup, right. I mean I have an objective function, so can I go and optimize that and find theta? I mean let us forget about what is the functional form of theta now is, there are still some questions I can ask in the general setting. So can I just take this and go optimize the theta, or maybe I should write it slightly differently so that it helps me later. Okay, there you go. This makes it easier, right. So this target, right, minus my current estimate, so this is the error, right. So target minus current estimate is the error, so I take the square, and so instead of, I mean writing it like this does not fit with our target minus estimate formulation that we had earlier, so I just flipped it around. Since it is squared error, it is okay, right. So is there any problem in trying to optimize this? Huh? There is a problem, there is a very serious problem. What is the problem? Huh? even before that. Even before we talk about solution techniques. Huh? Exactly. I don't know what V pi of s is. If I know V pi of s, I have no problem. I don't even have to learn anything, right? I put V pi as my target, right? I don't have the target. What will I learn about? Correct? Okay. So we have to find out way of specifying the target. Right? So what will be a good target? We spoke about this. It's the same thing we did in the tabular case. So GT will be what? That will be make it Monte Carlo. Right? So what else can you do? Yeah, you see?
We are essentially using a lookup table again
Where?
for V pi.
No,
Then how will you
we don't know V pi. That's what I told you, right? We don't know V pi. See, classically, if for regression problems, you would assume that you have data of the following form: some x and f of x, x f of x, x f of x, and then you go and learn f hat x. Correct? So that is the normal assumption that you make. But here, the training data will not be of that form. The training data is going to be of what form? Will be trajectories. The training data will be trajectories. I have ST, AT, RT plus 1, ST plus 1, AT plus 1, RT plus 2, ST plus 2, AT plus 2, AT plus 2, RT plus 3, and so on and so forth. That is how my training data is going to look like. Nowhere I am going to tell you, okay, here is ST, here is V pi of ST. Right? So this is the difference. So in classically in regression, the training data will be x comma f x pairs, and from here you will learn some kind of f hat x, right. Here for RL, the training data will be right. So somehow from this we need to learn V hat. Correct. So the training data should start looking something like this, right. From here I can create, here is one set of training data I will create, right. Whatever is the state ST, right, comma, that is the first data point. The second data point will be like that, right. So I will create data points like this and I can use it for training, right. So alternatively what can I do? Right. So this is how I will create training data for my, if I am going to use my regression as a black box, right, my training data for the regression look like this, right. So this seems to be a little acceptable, even though there are problems here, but this seems to be a little acceptable than that. Why?
Using the same function again in the training data.
What is the problem with that?
Might be zeros over there. That hasn't been explored yet. There might be
So what do? You go back and do it again, right? That is where you get into the problem, because what you are now setting up is a non-stationary target. So I will make up a set of training data like this, right, or let us say I will do one training data like this, right, and then I go back, I will update the thetas, right. So I will get a new estimate for my parameters theta, and then I come back and try to do the same sample again, it will be a different value, right, because I updated my theta, right. So this will essentially, this will be theta old, right. So I will be using the old theta, I will make a prediction, I will make a target, right, for my S1. So VS1 VST should become this, where this value was computed using the old theta. Now I updated the theta, right. Once I do this, I update the theta, I go back and look at the target for ST, it will be RT plus 1 plus gamma V hat ST plus 1 comma theta nu, right, it will be a different target, right. So I am essentially trying to shoot a moving target, right. So my targets keep changing after every iteration of updation, so it is not like I can actually converge to that, right. So a lot of people thought this is all hookum, right. I mean, how can I use RL to train a neural network, because I am shooting at a moving target, right. So people say, oh, RL won't work, blah blah and things like that, but then of course we always have this existential proofs. So luckily Jerry Tesaro never heard of all of these convergence results and stuff like that, and so he fired up a neural network that learned to play backgammon, right, not a simple single neuron or anything, it was a very complex neural network. So he trained a neural network to play backgammon, so people know that it works, right, but it seems to be pretty crazy that it actually works. And later on there are lots of results that show that with linear parameterization, right, we can show convergence even with this kind of an update. The one condition you need is that it should be what is the important condition I said? On policy. Sampling on trajectory, sampling on policy. So as long as you are being on policy, you can converge. So that was shown, right. So now we even have results for off policy updation, right. Very recent things, people have shown some kind of stability for off policy updates as well, right. So a lot of work is being done in this space, okay, because this is such a counterintuitive thing for people doing regression, right. So every time I look at the data, right, as soon as I use the data once, the data is going to change, right. So I can't say that I have a stable convergent point, but people have shown that this actually happens because of the way the dynamics of the system is set up. In fact, the way you show that is that with the function approximation also, the TD updates give you a contraction, right. So we showed contraction long time back, right. So you have to show that eventually this, even with the approximation, it is a contraction under certain conditions on the approximation. So that is essentially how people show this. This also works, right. So any questions so far on this? Okay. So how many of you are familiar with using gradient ascent or gradient descent to learn to optimize functions? I expect every hand to go up because we talked about it in policy gradient. Yes, can I assume that everybody knows this stuff, right? Otherwise flip back to reinforce. So we talked about all of this in the policy gradient thing, right. So in the policy gradient we did ascent, right. Why did we do ascent, gradient ascent? Because the function that we are dealing with there was the performance, right, and we want to maximize the performance with respect to the parameters theta, right. But the function I am dealing with here is the error. I want to minimize the error with respect to the parameters theta, so I will go in the opposite direction of the gradient, right. In policy gradient we went in the direction of the gradient, here I will go in the opposite direction of the gradient till I try to get to the lowest point, right. That is one of the popular ways of trying to minimize mean squared error, right. And a very popular variant of gradient descent is stochastic gradient descent, so that I do this on a point wise basis. So I mean, as soon as I get a single point estimate, I go in the opposite direction of the gradient I estimate there, right. So essentially what I can do now is have a truly online TD with function approximation implementation. So every time I go to a state, right, every time I do not do the summation business here. So every time I go to a state, I form this estimate, right, give it to my SGD optimizer, right, it takes a step, right. Now I have a new function. So now if I am going to do that at every time step, I can start calling this as theta t, right. So essentially what I am going to start doing now is I am going to say my theta t plus 1 will be theta t plus some alpha times gradient of the error, right, where the error is computed as whatever. So what do you want to use? Right. So this is gradient of the error function evaluated at theta t. Make sense? This will be my update rule. So one thing to notice there is that all the computation there is not v hat of st plus 1 theta t plus 1, it is v hat of st plus 1 theta t. So depending on the actual form you choose for v hat, right, so you will have different ways of computing this gradient, and you can compute this. Once you compute the gradient, you can actually make the update. So any questions on this so far? How many of you are following it? How many of you are completely lost? Anyone completely lost? Huh? Is that?
That is ascending question.
Any questions? Good. So let us move on. So there are many ways in which you can choose this parameterization, right. So the theta.